Okay, so we are going to finish chapter 6 today. Chapter 6 has us talking about a binomial probability distribution. And it's very technology heavy. I'm sure if you even perused looking at the textbook for reading this, it's kind of hard to read some of it because he talks about, and they have to have this in the textbook, quite honestly. How do I find the probability distribution by hand? How do I find the probability distribution by a table? And all of those things are rather labor intensive, but technology allows us to be able to focus instead on the finding the probability distribution easily, and instead of worrying about a calculation that might be wrong, we get to instead work on interpreting the calculation. So as we move through these last chapters, 6 through 10, when you find there is a lot of material focused on finding it by hand, finding it using a table method, right? You can rest assured that we're going to cut to the chase and we're going to be doing it mostly by technology. So what I would prefer that you do as part of your reading is at least going through and writing down the formulas that you do see in there, because we are going to need to be able to calculate certain things by hand, just not to the extent that the textbook is kind of showing you. Now, what we are looking at today is an extension of our probability that we were talking about on Wednesday of last week. Remember last week we were talking about the expected outcome of a game. You had a problem, and I hope I can get through today's lecture, and I would be happy to answer any questions you have over your homework. But there was a problem on the homework even, I think, talking about expected value of a life insurance policy, right? That's a typical time when we would see that as well. Expected value, the average cost, let's say, or the average expenditure that you would have is something that's a very common thing. I can see that being used in businesses and all sorts of things like that as well. So expected value, understanding how probability plays into what we are looking at in statistics. And now we talk specifically about a binomial probability distribution. So in the expected value probability model, we had several different outcomes with their associated probability, right? We were talking about getting a certain roll for a win, a certain roll for a loss, a certain roll for a push, and each one of those had their expected probabilities. Well, today what we're going to focus on are the binomial probabilities, and binomial means two, right? There's only two outcomes, and we have all sorts of things that we can model in that fashion, just thinking of a binomial distribution. Which soda do you prefer, Coke or Pepsi? Are you happy with the government? Yes, no. You know, all sorts of things that can be modeled as binomial distributions. So what we want to talk about is this idea where we have circumstances where only two categories are outcomes, right? So acceptable versus defective, survived or died, right? Those are outcomes that we would be looking at. And if you came in late, could you please go back to the back of the room and get the paper that I handed out for the or I made available for our notes. Now, when we have our probability, in order for us to claim that we have a binomial experiment, we have 4 criteria that have to be met. And all of these criteria have to be met. So if one of them is not met, then you cannot claim this is a binomial distribution. The first one in our set of rules has to do with, is there a fixed number of trials? Is there a fixed number of trials? All right, and each repetition of that experiment is what we would call a trial. The next thing has to do with, are the trials independent? Remember what independent was used for last week? When did we need to know if two events or multiple events were independent in order for us to be able to use what in probability?
Addition.
Multiplication is independence, right? Multiplication was independent, right? Was the probability of one of my kids having red hair affecting the probability of another kid? No, right? Addition and subtraction use mutually exclusive or disjoint. Remember, they're not the same. Okay, so independent, right? Are these events, is the probability independent? Okay. For each trial, the third requirement says that you also have to have two mutually exclusive outcomes. Remember, that means they can't overlap. All right, we cannot overlap. In other words, you either have success or you have failure. All right. And then the fourth criteria that must be met is that the probability of success is fixed. Okay, it doesn't change with each trial of your experiment. Now, I want to back up and talk about for just a second quickly for success or failure, depending on what your trial is, depending upon what your experiment is, success does not always equate to positivity things, like positive things, like happy things, okay? If I am testing the death rate on something or the morbidity on something, okay, then to have success would imply that something happened to cause death, right? That you would have some sort of death on that. Just understand that success isn't always, the happy thing. It could just mean it is the, the outcome that you were looking for in the experiment. Now, let's take a little time and let's practice. You have these on your paper, I believe, as well. We have a couple of things here that we want to practice, because in order for us to be able to claim some sort of binomial distribution, we must meet these four criteria. So let's talk about that first one on there. It says you're rolling 5 dice and you need to get at least 2 sixes to win the game. Okay, that's the scenario. So let's just go through these scenarios, the requirements. Are there a fixed number of trials?
Yes.
Where does it say that?
You're rolling 5 dice.
That's how many I'm.
No.
Ah, right. I know there was a number in there. There was a number in there, but there's no set number of trials, right? There's no sample size. There's nothing in there that tells me how many times am I doing this. I just know I'm rolling 5 dice and I'm trying to get 2 sixes out of it. So right away, we didn't meet the very first criteria. There are no, we don't know how long to play it. So it is not a binomial distribution. There's no fixed number of trials. See how we're doing that? Okay, let's look at the next one then.
No.
Right.
You have more than 2 outcomes.
All right, so let's go through that because I'm just going to start from the top, right? Number 1, is there a fixed number of trials if we record the eye colors found in a group of 500 people?
Yeah, because
Yeah,
it's
500.
500 would be the trials. That's right. N is equal to 500. Might be a good idea to keep track of that. So there are a fixed number of trials. That N is equal to 500. Are they independent? Yes, they are independent, right? If we are looking at eye color found in different people, the eye color of one person does not affect the eye color of another person. Typically, people are independent, okay? Are they mutually exclusive? Are there, no, wait, I should say that differently. Are there only 2 outcomes? That's what I should say. No, Erica told us that, right? How many outcomes could you have for eye color? Lots, right? More than two. More than two. Now, another way to phrase this question would have been, maybe you wanted to research whether more people are blue-eyed on the East Coast or something like that, right? The outcome that you're looking for is either blue-eyed or not. That's two outcomes. That has a success or a failure. That's still talking about eye color, but I have now limited what I'm looking for, okay? But the way that this is stated, that we record the eye color of 500 people, that is not a binomial event. How about the next one? A manufacturer recalls a doll because 3% have buttons that are not properly attached. Customers return 37 of the dolls to this toy store. And is the manufacturer likely to find any dangerous buttons? So we're just trying to figure out, are there a fixed number of trials? What are they? Yes, there's 37 trials, right? The sample size is 37. I want you all to get used to writing that down. Number one, yes, n is equal to 37. Are they independent?
Yes.
They are. The dolls are independent of each other, right? The likelihood that one doll has a button missing should be independent of whether or not another doll has ours is defective. Are there two outcomes? What are they? Right, defective or not, right? Two outcomes. Is the probability of success fixed? Yes, it is. And what is the probability that it's defective? Says it right there in the problem. What is the probability? 3%? Everybody see that? That the probability is 3%? And that doesn't change from doll to doll. They're saying overall there's a probability that they're defective at 3%. Okay, so that is considered out of the three that we've looked at so far. That's the only one that came up being a binomial model. All right, and we need to be able to practice identifying all of those components out there, out of that, right? The fact that they're 37 is the sample size, that's the number of trials. We need to understand that the outcome is either defective versus not defective, and the probability of success, right, would be the 0.3, the probability 0.03%. So the next one says a city council of 11 Republicans and 8 Democrats picks a committee of 4 at random. What is the probability that they choose a Democrat? All right, is there a fixed number of trials?
4, yes.
Yes, so n is equal to 4. Are they independent? Yeah, because they're people, right? Okay. Are there 2 outcomes? What are those outcomes? Republican or Democrat. And is the probability the same?
No,
Why do you say no?
because there's more Republicans than Democrats in the initial population.
That shouldn't matter. Proportionally wise, that should not matter. All right. Just like if we had, if you've done a sampling right, it wouldn't matter what the proportions were. You sample proportionately, right? So you would have to make sure that in the city of Waco, if we are, 30% independent, 60% one other, then you just make sure that you have sampled enough to where you have met that similar proportionality, okay? It's not exactly clear in this statement. And one of the things that we didn't talk about in probability, and it kind of is a good example of us being able to talk about it here, has to do with replacement or sampling without replacement, sampling with replacement. And those terms are, they help you understand what's going on. So let's say that we have 19 names, right? We have 19 names from the people in this group that we put into a hat, right? 11 Republicans, and 8 Democrats. And I put all the names in the hat because that would just be the easiest thing to do. And we shake the hat up and then we draw a name, correct? That would be simple random sampling, wouldn't it? That's an example of simple random sampling. So if I have, if I pick one name, right, out of 19, right? What's the probability that I pick a name, one of these names out of 19? I have some value, correct? Okay, so now I put that piece of paper down, and I'm going to go back and I'll shake up my lot, right? My bin, it has all the names in it, and I draw another name. Right? So now I just drew another name, but how many names are in the bin? So 1 out of 19, right? That value is not the same as 1 out of 18, is it? So the probability is not the same for each draw that I take, is it? It is not equally likely I'm going to pick one of these names as it is the other, because each time I am not replacing the value, right? I'm not replacing the name, it's without replacement. And therefore it changes the denominator, doesn't it? Which changes the fraction, okay? So when you see things that say with replacement or without replacement, that's what they're referring to. If I shake it up, I draw a name, right? And I keep the name out and I don't put it back in, that's without replacement, right? Okay, or if I put it back in, that's with replacement. Okay, that's the difference. So in this particular one, what we're trying to hint at in it is the reason it doesn't pass this test, the probability distribution, the binomial distribution test, is because we are assuming that this is a without replacement. That would kick it out. Okay. The other thing that we're going to kind of look at too, and we really delve into this a little bit later on, is it's almost too small of a sample size for us to feel confident in it. But anyway, we're trying to highlight just a couple of things in this one. So then the last one is right here. This one says, in 2002, Rutgers University found that 74% of high school students had cheated on a test at least once. Principal conducted a survey and got responses that admit to cheating from 322 of the 481 students. Is there a fixed number of trials here? 481 students. Very good. The sample size is the 481 students.
So the last one, so is it or is it not?
It is not a binomial. It failed the last criteria.
Because of the last
Yes, because of the last one. And so Rutgers, it is a fixed number of trials because the number of trials is 481. Is each trial independent? Are these independent? Yes, they are independent. Are there two outcomes? What are they? Cheating or not cheating, right? Okay. And is the probability the same? They gave us the probability too at the problem. 0.74, yeah, 0.74 or 74%. So this one is considered a binomial distribution because it met all 4 of those criteria. Okay. So most of the time it's going to be, most of the time it will be meeting the criteria, but you need to check for it, right? It's one of those things that you want to check just to make sure that it has met the criteria. Okay. Now, here, there's a slot on your handout that I gave you for you to be able to fill in the variables that we're talking about here. So we are going to let little n, lowercase n, in this particular case denotes those fixed number of trials, which we can see is going to be the sample size as well, lowercase n. X represents the number of successes in trials. The number of successes in trials. This is where we're adding another p into our growing list of variables. Notice that little p there, that lowercase p is representing the probability of success. All right, so we're gonna let little p represent the probability of success. And then in this textbook, which is why you see me mark through that Q, we're gonna let the probability of failure then be 1 minus p. Because if you only have 2 outcomes, and you know what the probability of success is, then 1 minus success is failure, correct? All right. So 1 minus p would be the failure. And then we want to keep in mind that capital P of X is our probability of that success, right? The probability of getting exactly X successes in N trials. So it's the probability of success for whatever we're looking at. Probability of getting exactly X successes, I should say. All right, question?
So like lowercase p is probability of success in one trial, and then capital P is probability of success in the whole trial?
No. Lowercase p is the probability of successes in trials, right? Of just, lowercase p is gonna be that 74% that we just saw,
Okay.
74%. And then capital P is the probability of my variable that's changing, given the parameters we're looking at. What's the probability I'm gonna get this if I know the overall success is this? Okay. Okay, now, this is where that formula that I have right there, right? This formula is the one that shows up in your textbook. All right, I'm not gonna ask you to do anything with this formula, I don't believe. I'm not going to. So I just want to show you this formula. You're gonna write it down. This is the, if I had to calculate it by hand, the method that I would use. And the thing about this is, and we don't cover this, is in change X has to do with a combination, and it's a counting technique. How many ways could I get, I don't know, 3 girls out of 5 children, right? It's how many ways could that combination show up? All right, and we don't spend a lot of time, we don't spend any time on that part of probability in this class, which is why we don't really use this formula, because we have a handy calculator that does it for us. That P would be our probability of success raised to whatever we were looking at, right? That's our independent part right there. And then because the two don't overlap, I guess we can talk about the failure as well, all right? But what I want you to know moving forward has to do with this. So the formulas that we are going to need, and we will have to actually calculate these by hand. Okay, so you want to have them written down. These apply when the binomial requirements have been met. We're going to be able to calculate the mean of our distribution, and that should say, another time you would see this is mu sub x. I may want to add that in here. I'm going to add a little x there. Mu sub x, sigma sub x. That's telling me that it's the mean of that variable. U always stands for mean. X, little x is talking about the variable that we're looking at, the mean of the variable. Now we can find the mean of the variable by taking the average, or by taking the sample size times the probability of getting that. So Michael, to your question, if it's kind of like this, if I randomly selected 100 widgets and 10% of them are defective, how many would I expect to find defective? 10% of 100, right? So I would expect to find 10, right? So that 10% is what we expect to have happening, okay? Then the standard deviation. Now we are going to, I've said I won't ask you to calculate standard deviation, but I might have lied on that just a little bit, right? I'm not going to ask you to go through and find that normal standard deviation like we did at the beginning. What I will be asking you to find are these, is the standard deviation in this fashion right here. This says that to find the standard deviation of the variable x, I'm going to take the square root, and we have to all practice how to find the square root on our calculators. And underneath there, I'm gonna multiply the sample size times the probability of success times the probability of failure. NP 1 minus P. You multiply them all together. Order of operations tell me to do what's under the grouping symbol first. I have to multiply all three of those things together, and then I take the square root. That's the standard deviation of our random variable that's changing. Okay, so I will be asking you to do that. You will have to do that. And then should you need it, if I know what the standard deviation is, I can always find the variance by squaring the standard deviation. That's what that says there. Okay. So these are the formulas that we're going to be using. And the other thing that we have to just make sure that we understand is before we move further, we kind of touched on this the other day. It has to do with these inequality symbols and what we mean by the inequality symbols, right? So if I have at least, right? If I have at least or something like that, greater than or equal to, then that means that I would have that number or more, correct? That's what that line underneath it means, is the equality symbol in addition to the inequality symbol. When I don't have that line under there, it means that I can't include that number. So if I wanted to eat at least three cookies, right, then I would eat three or more, right? If I wanted to eat less than three cookies, I would eat, 0, 1, and 2, correct? Okay, so just remember those. All right. Now, let's get into a problem here that we want to look at. So for this particular problem, and this is going to be not on your paper, but this is one that I want to work. So I have two problems I believe that I want to work with you here, right? And it says, according to Harris International, 50% of all adult Americans believe divorce is acceptable. Right? So there's our statement. According to Harris International, 58% of all adult Americans believe that divorce is acceptable. That 58% is a probability. It's a percentage, right? It's actually talking about our population, because in the very next sentence it says, all right, in a random sample now of 500 adults, determine the mean and the standard deviation of the adult Americans who believe that divorce is acceptable. Okay, so if I'm just randomly selecting 500 adults, how many of them on average do you think are going to say that divorce is acceptable? So what we're looking at here is what outcomes do we have? Is this a binomial distribution? Is this a binomial model? Are there a fixed number of trials that we want to look at? Yes? 500, right? So let's just take a minute and let's write down that N is equal to 500, okay? So there are a fixed number of trials and those trials are 500. Are they independent? Are each trial is independent because these are separate people, right? Okay. So I would say 1 would be the trials. 2, yes, they are independent. Are there only 2 outcomes? Yes. Right? It's either it's acceptable or not. And is the probability the same for each of these experiments? Yes. So little p is equal to 0.58. So the 58% that was given in the problem is the probability of success. Now, get your calculator out of choice. And we want to know, what is the mean then? So if I talk to these 500 people, and I know that on average, they think that there's about 58% of the average person thinks divorce is acceptable. In a group of 500 randomly selected people, what's the average number who are going to think that it is acceptable? So the mean, mu sub x, is equal to N times P. That's the formula we're working with. That is what we expect to have. That's our average expectation. In this case was 500. P is 0.58. And so on your calculators, you just need to multiply 0.58 times 500. And to the nearest whole person, what do we have?
290.
That's right. Was it a whole number?
Mhm.
Oh, okay, I wasn't sure. 290. We would expect then on average, right, if 58% of adult Americans, if the population of America, if 58% of people believe divorce is acceptable, we would expect in a group of 500 people to find about 290 of them believe divorce is acceptable. Okay? Do you want me to repeat that? You can write it for yourself then, right? That interpretation? Good. How about the standard deviation? Standard deviation looks like sigma x. This is going to be the square root of 500 times 0.58 times 1 minus 0.58. Okay? 1 minus 0.58 would be what? 0.42. So it would be 500 times 0.58 times 0.42. And then take the square root of it. Everybody needs to do that on their calculators right now. If you don't have a square root symbol and you're using a cell phone, turn it sideways. You get the scientific one. Okay, let's take a minute. I want everybody to make sure they can get it. You multiply all three of them together. So there's a little bit of a learning curve on your calculators as to when you're supposed to hit the square root symbol. It just kind of depends on what model and device you're using. But we end up with something like 11. All right, so you want to make sure that you can get this value. On your calculator. Does anybody have a question on how to do that? Is everybody able to get that on their calculators? Yeah? Even on the cell phones? Erica, you got it? Okay. Michael, did you get it? No? All right. So whenever I'm trying out new calculators, I need to know what I'm gonna yell. Talking to everybody too, okay? So take what's the square root of 4? 2. All right, so put 4 in there. Hit clear. 4. Now hit square root. The square root symbol. So that's the order you want to put it in. So you put the number in, then you hit the square root. Some of them you have to put the square root and then the number. So I always take a number that I know and see which process it is, okay? So again, somebody interpret the mean here. What does it mean?
What does the mean mean?
Yep, so in context to this problem, you tell me, what does it mean? What does the mean mean, Danielle?
290 out of 500 people find that it's acceptable.
Almost. Does anybody want to add anything to that?
Sample of 500 500 people, you would expect about 290 of them to find divorce acceptable.
So you've added to what Danielle said, but there's still one important part that's missing out of all of this. Does anybody want to keep trying? We're missing one thing.
Random sample, no?
What if the probability from the population was 0.57? That we would have a different value, would we not? So we have to put in there that 0.58 or the 58%. Right? That goes with what we're talking about. Without that 58%, we would never have gotten to the 290. Okay? We are claiming, right? We are taking the claim that says 58% of Americans believe that. So assuming 58% of all Americans believe divorce is acceptable, right? You see how I just regurgitated the sentence there, but I put an assuming in front of it? Assuming 58% of adult Americans believe divorce is acceptable, we would expect about 290 of them out of 500 to believe that divorce is acceptable. Okay? That all of that has to go into that sentence for our interpretation. And that was the only thing that y'all were missing, is that population's proportion, basically, right? Very good. Now, that's what we would expect to have happen if we have this group, right? That I would find that, okay, on average, I'm going to get about 290 of them that are going to say this. That's a pretty finite number, right? That's a pretty exact number, 290, isn't it? It's an equality statement. It says that I am going to get 290 people. Wonder how likely that would be. So let's instead look at this and say, well, what is the probability of finding at least 275 of them? Right? Because we know that if we on average can find 290, where does 290 fall on a distribution, right? If that's the average. It should be the middle, shouldn't it? Yeah, if we're talking about an average here. So what we're saying is, what is the probability, capital P, that I find at least 275 people who believe divorce is acceptable? Remember that variable is changing. The variable X is the people who believe it's acceptable. Variable X would be our successes, right, out of the sample. So what's the probability that I have at least 275 people now who believe it's acceptable? Okay, that's a little bit more of a broader range, right? That allows me to be able to look at it maybe a little bit less of a finite value. Now, what I want you to get in the habit of doing is we are assuming that we have a normal or a bell-shaped distribution here, okay? And because we're talking about the mean, right? The mean of our bell-shaped distribution should fall here in the middle, which we think was, which we said we would expect to have 290 people out of the 500, right? That's the middle. Yes? Do we understand what I'm just drawing here? This relates to what you were reading, Erica, maybe? All right, so this is our distribution here, and I want to know, I wonder what the probability is if I have 275 or more. If I were to just draw a line representing 275 on this graph, where would it fall in relation to 290? Where would 275 fall? To the left of 290, correct? It's just shy of 290, right? So this would be 275. And I want to know, what is the probability of 290 or more, correct? So pictorially, I've just drawn a graph representing the probability that I'm looking for. And we can say with assurance that the probability under this curve, the total probability in a model has to be equal to what? Total probability has to be equal to what? 100% or 1, right? 100% or 1, right? Okay, so what I'm looking for then would be all of this probability that's going to be to the right of what we're looking at. Okay, and there's a reason, right? I don't just make you draw pictures just because they're cool. There's a reason we're doing this. So I'm going to go now to StatCrunch. And remember how I told you last week we were going to be adding another calculator. So our calculator came under stat calculators, right? Our custom calculator from last week. Well, if I hover my mouse here, you'll notice there is a binomial calculator. So when you're making this list of things to use StatCrunch for, and you're writing the heading, chapter 6 is about expected value and binomial distribution, we're going to use the binomial calculator for the binomial probability distribution. So here's my calculator. The sample size that we're looking at was, what size sample did I have? 500? Okay, so 500. The probability of success in this case was 58.58. Now I'm looking for this again, right? I'm fixing to fill in that probability statement, which I may go write down. We're looking for the probability that I encounter someone who had success greater than 270. 270, what was the number? 275. Now looky there. A lot of things going on with this picture, okay? A lot of things are going on with this picture. Number one, what is this box down here that's got 0.919 in it?
Probability.
It's the probability, that's right. That's always going to be the probability. That box is always going to be our probability, okay? So the likelihood that I find more than 275 people out of a group of 500 who believe that divorce is acceptable is about 92%, right? Okay, now notice also this graph happens to be shaded red and green, doesn't it? Or red and black, right? Do you all see those colors? Anybody not see those colors? Yeah, my husband's colorblind, that's what I'm asking. Okay, right? So red and black. Notice that if I were to probably hover my mouse right there around this position, what happens? Anything? No, nothing. But that's the line that's actually changing, right? That is about 275 on this graph, just like we drew. The reason this is important is because this picture here supports the sketch we made, doesn't it? That I was shading to the right of my probability question. And it can help you make sure that you've actually told the calculator you're looking in the right direction. I'm looking for greater than this number, not less than this number, right? Okay, so this says that we would expect, you know, what, 92% to find, to think that that was acceptable. Okay, would it be unusual for us to find in a random sample of 500? Would it be unusual for us to find 310 who believe divorce is acceptable? Well, let's write that down first before we throw it into the calculator. By the way, if I come back to my paper, because this is what I'm writing my stuff down on as I work through the problems in my math lab, I've got this sketch here on my own notebook paper, and I would then, after I use the calculator, find write down 0.92 or whatever rounding I'm supposed to do. This helps you at least be able to go back when you're trying to study. It helps you be able to come and ask me a question, right? If you've done it all in your head and all directly into the calculator, you have nothing to be able to troubleshoot, okay? So get it out of your calculator and put it down here first. So how would I write the statement then? Would it be unusual to find in a random sample of 500 adults, or 310 who believe divorce is acceptable? How do I write that first?
P of X greater than or equal to 310.
Is it greater than or equal to 310? It's just equal to 310, right? In this statement. Right, it's in this statement, it says, okay, 500 people, what's the probability? 310 of them believe divorce is acceptable. I'm not giving a range. I want to know 310, that's it. So we would instead put an equal sign here. And if I'm looking at that graph, I know that the mean is at 290. 310 is to the right of 290, and there's no shading. I just want to know what's the probability I get 310. That's it. So coming back to this calculator, I'm going to change the probability statement here to equals 310. And you can see there's only one little red bar in there, right? Everything else is black. Okay, here's our red bar over here at 310. What is the probability of getting exactly 310 people out of 500? All right, 0.007. 0.007. If I change that to a percent, that would be less than 1%, right? It's 0.7%. It's not even 1% yet. So would it be unusual? Would it be unlikely to find 310 people who believe this? Yes, because it's much less than 5% or 0.05, right? Most of the time, that's what you're going to have, especially when we have that equality statement. If we have an inequality statement, we have a little bit more room, right? This is saying, what's the likelihood I'm going to meet 310? That's it, nothing else, right? So that's a little less likely to happen. Very good. So do you see what we're using the calculator for? Can you see why I said that people, I don't have a problem with this either, will maybe write down some notes about the calculator, what little blank is what, all right? It's also why I want you to keep sketching the graph. So let's look at another one here. Okay, so different example. Suppose that 20 donors come to a blood drive. 6% of all people are universal donors, or in other words, O negative. What's the probability of getting 2 or 3 universal donors? So let's go through. We have to verify first that this is a binomial model. So are there a fixed number of trials?
Yes.
What are they? All right, so we have 20 people that come, right? There's a fixed number of trials. What's next? Are they independent? Why? All right, they're independent because these are all people, right? Okay. Are there 2 outcomes?
No.
Well, no, I know why you're thinking no, but yes, because of what I'm asking. What's the probability
If
of a
they
universal?
are or not.
Yes,
Yeah.
Okay.
yes, there are more than one outcome as far as blood types. That's not what we're asking. So either universal or not, O negative or not. What's the probability of success? What variable do I label that? What variable do I assign to the 6%? Lowercase p, okay, lowercase p. What they're saying is that, all right, nationwide or maybe worldwide, I don't really know, 6% of all donors are 6% of all people are universal donors. Just that's the big picture. That's the 30,000-foot picture. 6% of all people are universal donors. Now let's bring it down to just 20 people. In a sample of 20 people, what's the probability of getting 2 or 3 universal donors? Now the statement says the probability of 2 or 3. And I write that as an in-between statement, right? Because if I can get 2 or 3, that means I'm going to get 2 up to 3, correct? I can have the minimum of 2 up to 3. That's an in-between statement. And so that looks like okay, we know we have a middle here. I didn't draw everything out, but I know that I've got 2 here, and I would probably have 3 here, right? Something like that. If it was a normal distribution, that's kind of what we would be looking for. Now, to go to the binomial calculator again. Remember, I think I showed you this. I may not have. I'm thinking I did. There is a between button here on our calculator, just like there was on our custom calculator. And I click that custom or the between, and now I change my sample size to 20 people, 0.06 for the probability of success. And I have the variable that's changing, right? That's the people who are no negative. So that would be 2 to 3. Then there's no option in this to do any other inequality symbol, right? There's nothing, there's no equals, and there's no changing of the inequality. This is it, your choices. So what is the probability out of 20 people that 2 or 3 of them are O negative? 31%. So would it be unusual for me to get in a group of 20 people, 2 or 3 of them that are O negative? No, right? That would not be unusual. Could you describe for me the distribution that we have here? It's skewed. It is definitely skewed right, correct, okay? And we have sort of an issue now when we start talking about unusual versus not unusual, because our unusualness says that we think things, if they happen, if they fall between 95%, right, in the middle, 5% on the tails is where we think things don't normally happen, right? That's the unusual part. What model was that based on? It starts with an E. The empirical rule, correct. And the empirical rule was based on a normal distribution, correct? I don't have a normal distribution here, and yet I'm trying to apply a property or a principle based on a normal distribution, right? So let's see. It's skewed in this way, and I have a sample size of 20. And the overall, right, that 0.06 has to do with the population, right? So worldwide, I'm assuming, okay? So let's look at the distribution for just a second. What happens if I say, maybe I want to encounter 50 people? Let's see what the shape of the distribution looks like there. Compared to the 20, what do you see? Is it still skewed? Give me your thoughts really fast. It's not as skewed, right? Would you all agree with that? All right, so this is getting promising. How about at 100? Just looking at the shape. We're just talking about the shape right now. What would we say?
More bell shape.
It's moving more towards bell shape. Yeah. I think I could change this to, I don't know, 200. That's much, much better. My bars are also getting higher, aren't they? Right, looks like to me they're getting taller. All right, so this is an important concept that we kind of cover in the, we're previewing it, it's called the central limit theorem. But it basically says that if my sample doesn't come from a normal distribution, right? Then I can increase the sample size and get it to the normal a normal distribution. So then I can move on and I can apply the properties that we're learning that apply to normal distributions. Okay, then they're valid. So all I have to do is make sure that my sample size ends up being large enough for me to apply the central limit theorem on. Okay, and so there was a little blurb in your textbook that talked about. And I kind of skipped this part, I suppose. But there was a little blurb in your textbook that talks about this idea right here. It says that if a fixed probability, right, if our fixed proportion, P, as we increase the number of trials in our binomial experiment, then the probability distribution becomes more bell-shaped. And we just saw that, right? We just watched how that happened. So what we do is, if I don't want to go through and play with numbers and determine whether or not my shape is just, skewed or not, we have a little formula right here that says NP times 1 minus P has to be greater than or equal to 10. And that gives us a quantitative measure. It gives us a formula for us to be able to use and check and say, if I don't know anything about my distribution, I can throw it into this formula and I can determine if it's greater than or equal to 10, then I'm all right. I don't really care what the distribution is going to be because everything will work out fine. If it's less than or equal to 10, if it's less than 10, then I maybe need to look into it a little further. I maybe probably need to just increase my sample size. Okay, so let's come back and we'll just finish this off for a second. We know that, I don't remember what our number was, but I think you said 31. Is that what you said, Erica? 31, 32?
Yeah, 31.
All right, so that was our probability here. So let's kind of, before we go any further, because we don't really know if that is well, we know now. That's not the shape, right? But I could have checked it. I could have checked this number before. So if I want to check for the shape of our distribution, I'm going to take N, multiply it times P and 1 minus P and see if it's greater than or equal to 10. So N in this case was 20, P is 0.06, and 1 minus P is 0.94. What does that equal? One point one something or other?
1.128.
1.128, I think is what, well, that's much less. That's not even close to being greater than 10, is it? Is 1 greater than 10? No. So all we were able to do from here is see that I can take a formula, right? I can take a rule. That's why we have formulas. And I can take my known values, my N and my P. If I don't know what if I don't know what the shape of my sample is, and I can throw it into this formula, NP 1 minus P, and I can see because it didn't meet the requirements that I probably have some sort of skewed distribution. And we saw that from the calculator, didn't we? Okay, so this is a way for us to check that distribution. Now we'll go into this much more in detail. So this is kind of a preview as to why am I checking this NP 1 minus P? Okay, and the reason I'm checking it is because if I don't know anything about my sample, right? If I don't know what the shape of my sample is, then I can't technically apply these normal rules to it. All right, now, we can come over here also and we can kind of come up with, let's practice the mean and the standard deviation based on this scenario. So the mean is found by multiplying n times p, correct? So n times p was just 20 times 0.06, which is equal to 1.2. Okay, and how do I find the standard deviation? We'll practice that really fast before moving on. That would be 20 times 0.06. 0.94, and then take the square root of it. You end up with something like 1.1. Yeah.
1.062.
Okay. All right, so all we're really saying here for this problem, I just kind of wanted us to practice for a second. How do I find that mean? How do I find that standard deviation? So in other words, we would expect about 1 or 2, right? With a population of 6% O negative. In a sample of 20, we would expect 1 or 2 people to be O negative. Remember, that's how we interpret it. Okay, talking about the 6%, then bring it down to the sample size that we've got. Well, we know that this is not normal distribution. Let's look at this scenario really quickly. So this scenario says, okay, we haven't changed our populations, we haven't changed the 6%. 6% of people are still O negative. That doesn't change. Okay, we're still going off of that idea right now. All right, so, but what we are changing is, so instead of maybe us looking at a local MCC blood drive that only contained 20 people, okay, let's broaden that out and let's say, well, what if I have a nationwide blood drive and I am going to collect, I want to collect 1,800 or 1,850, that's how many, that's how much O negative I need to collect. And I'm trying to hit 32,000 people nationwide, right? So in our nation, we want to try to get 32,000 people coming to a blood drive. All right, we already know that this is a probability, a binomial distribution. So in terms of what we're looking at here, the question says, what is the probability of collecting 1,850 O negative people? How would I write that probability statement? P, capital P.
And X is greater than.
No,
Or is it just exact?
exact, right? This is the one where it says, I need 1,850. We all see that? It doesn't say I need at least 1,850. It doesn't say I need at most 1,850. It just simply says 1,850. That's an exact statement. So that is an equality symbol. That is equal to 1,850. What is our sample size that we are now using? 32,000. Okay. Now, if I go to my calculator, 32,000 is my sample size. Did the probability of finding an O negative person change? 0.06 didn't change, right? 0.06 doesn't change, and I need to go back to the standard one. So I'm looking for equal to 1850. There's an awful lot of black there, isn't there? And it's, notice that it's a smooth curve too, right? It's a little bit more, it's much smoother than the little sticks that we saw previously. Why do you suppose that is? Why do you think that it's more filled in? Because what?
Because it is so large.
Because the sample size is so large. Remember, each one of these vertical lines actually represents a discrete variable, a value, right? Okay, so I got 32,000 lines up there basically, all right? So what is the probability of getting exactly 1850? 0.0024. Does everybody see where that's at? So I want to hear you next time, right? So if the probability is equal to 0.0024, would it be unusual for me to set the bar if I am trying to, maybe I am the one who's coming up with this blood drive, and if I say, okay, we gotta get 1850 people, right? What's the likelihood of that happening? If I know I can get 32,000 people to come to the blood drive, what's the likelihood of me getting 1850? Really, really strong?
No.
No, it's not even at 1%, right? It's less than 1%. 0.2% is kind of unusual for me to get 1850, which is what we said before, right? It's kind of unusual for you to get an exact number. What would the probability then be if 1850 is my base number that I need as the event organizer of this blood drive? I gotta have 1850. Well, I'd probably be happy if I got 1850 or more, wouldn't I? Yeah? So what would the probability then be of more than at least 1850? Well, that messes it. What'd you say it was?
0.95.
0.95. So what is the likelihood then of getting at least 1850? 95%? So we would expect that if 6% of all donors are universal, or 6% of all people are universal donors, then I would expect to get about 1,850 or more out of a sampling of 32,000 people. So you see how we're looking at that now, all right? What if I wanted to know, okay, well, I want to kind of maybe make this a little bit more defined. I want to know what my boundaries are, let's say, in this. And remember that when we had our empirical rule, we've already said that when we are here at 95%, anything underneath that umbrella of 95% is what we would expect to happen. Anything outside of that would be unusual, right? Okay, so in other words, here, right, this is unusual. Here is unusual. And we know that 95% based on the empirical rule happened 2 standard deviations away from the middle, right? 2 standard deviations away from the middle. So this cutoff point to the left is going to be mu minus 2 standard deviations. And this cutoff to the right is going to be mu plus 2 standard deviations. Well, in context to this problem, how do I know what that boundary is? How do I know what I can expect 95% of the time in a sampling of 32,000? How do I find the mean of this sampling? How do I find mu sub x? U sub x was N times P, correct? So somebody tell me, what is N times P? That would be 32,000 times 0.06. Y'all are all pushing buttons, right? It's a race to see who can get me the answer first. All right, 1920, that is our mean. That's our expected average, right? If we're thinking of it in terms of that, in a sample of 32,000 people, we would expect that about 1,920 of them would be O negative. That's the middle, that's the average. How do I find, because I've got the mean now, how am I going to find the standard deviation?
N times P times 1 minus P.
That's right. N, P, 1 minus P, all under the square root symbol. And to the nearest whole person, tell me what that value is. Take the square root of it. All right, so 43. I'm gonna round up to 43. Yeah. So we have about 43 for the standard deviation. So here, if I know that I'm looking for a boundary, right? What's the minimum number of people I would expect, and what's the maximum number of people I would expect, right? It's an interval there. So the minimum number of donors to be considered usual is going to be 1920 minus 2 times 43. Right? That's the mean minus 2 times the standard deviation. What do you get? 1834. What do we get for mu plus 2 standard deviations?
2006.
2006. In the middle is our 1920. All right, so we would kind of look at this and go, okay, I know that if I have 32,000 people in a blood drive, okay, and I'm looking specifically for O negative donors, then it would be usual, right? I would kind of expect to see anywhere between 1834 and 2006 of those 32,000 people to have O negative blood. Okay, so it kind of gives me a range now, right? It gives me this boundary of times or of numbers for me to be able to look through so that I can determine unusual versus not unusual, right? Anything less than 1834 would be kind of unusual. If I encountered out of 32,000 people in my blood drive and I only got 1,700 of them back as O negative, that would be unusual because that's less than that, right? If in my 32,000 people blood drive, I encounter 2,200 of those people that have O negative blood, that would be kind of unusual, all right? So this boundary between usual and unusual just allows us to be able to look at the data maybe in different aspects. All right, you got homework over this, okay? If you have questions on your homework or on as you're going through it, send me an email or come and talk to me after class, okay? We didn't have our probability quiz.